In the next few lectures, we are going to start a new topic called linear programming. Before we talk about the details, I want to give you a kind of a high-level big picture overview of where we are at. So remember, in the second or the third lecture, we introduced something called convex optimization problem. And we said convex optimization problem can be solved in polynomial time, right? So if you recall a generic convex optimization problem is of this form. You have minimize f of x subject to gx less than equal to 0 and hx equals to 0 where f and g are convex, then h is linear, or usually people call it affine as well. Right? So this is the most generic form of convex optimization problem, and it's polynomially solvable. Right? And there are some special cases of this convex optimization problem. In the previous lecture, what we covered is a so-called, so this is lecture 3. What we covered is the M-constrained optimization problem where basically you don't have those constraints gx and hx, right? What you only have is just minimize f of x where the domain of x is in Rn. That's M-constrained optimization problem. So in the next few lectures, we are going to cover some special cases of this convex optimization problem. The first special case we have is so-called linear programming. Right? So that means the f, g, and h are all linear functions. Okay? As you can see, linear function is just a special case of convex function. It's very easy to see that. And another special case we will cover after linear programming is a so-called conic programming. Okay, so conic programming are also a special case of convex optimization. I will not talk about what it is right now, but a cone is a special convex set. Remember what we have talked about, conic Hall, conic combination, and so forth. Basically, in words, a cone is like if you take any points in this set, you multiply it by a non-negative number, and this ray will still be in this set. That is what a cone is. But we will talk about it in probably 2 or 3 weeks from now. So why do we care about those special cases? Why don't we just talk about convex optimization at the beginning, right? So the reason is that if you want to solve convex optimization problem, there are very generic algorithms to solve convex optimization problem in this very generic form, right? But in some special case, you can take advantage of the geometric properties of the problem to have a faster algorithm than treating the problem as a generic convex optimization problem. That's why we are covering those special cases. The reason is that this special case let's call it, they have some, quote, very nice properties. Usually those are some geometric properties. Okay, we can take advantage of. So the sequence we are going to talk about convex problem is as follows. We will first talk about the special case, linear programming, then we will talk about conic program, then you will realize for those special cases, we do have some tailored methods. Then after that, we will talk about this generic problem, which is this generic convex optimization problem. I just want to give you an outline first in terms of what we are going to talk about in the next, let's say, 4 or 5 weeks. Okay. So in this lecture, let's start with the linear programming. Okay. So what is linear programming? Here's an illustrative example. As you can find, we have only 4 variables. We are denoting them by x1, x2, x3, and x4. Right? So in the objective, you have some sort of linear function of x1, x2, and x3. And we can have some constraint. All those are linear constraints. Right? If you are thinking about applications, for example, in the first lecture, we talk about this diet problem. Remember that someone want to consume apples, milk, and bread, and so forth. You need to have enough consumption such that you have enough calorie, protein, and vitamin, and so forth. Right? So those problems are all in this form of a linear program. So if you take a look at this problem, it has different types of constraints, right? It has inequality constraints. For example, this is an inequality constraints. It also has equality constraint, like this one is a equality constraint. And we can also get some variable bounds, let's say x1 greater than or equal to 0, x3 less than or equal to 0. Okay. So if we write it in a very generic form, this is a generalized linear programming problem. Let's say we have a decision variable x is in Rn, right? Then the objective is to minimize C transpose x. Right? You can also do maximization, just change the sign to be a negative sign and so forth. And subject to constraints. So here we are writing the constraints in 5 different classes. Right? So the first type of class of constraint is a greater than or equal to constraint. You can assume you have a bunch of constraints where they are of the form AI transpose X greater than BI. So we are indexing the constraint through this set M1. And similarly, we can have less than or equal to constraint, strict equality constraint. And here are some simple constraints on variable bounds. Let's say X can be either positive or negative. Okay. Any questions for this generic formulation, generalized formulation here? Yes?
Could you rewrite like the selects the second 2 in terms of the first?
Yeah, exactly. I'm going to talk about that. So, okay, so that's just as Ari said, you can write the last 2 constraints in terms of those constraints, right? Because you just choose A to be, for example, EI. EI would be the ith entry of that vector is 1. All the other entries of that vector is 0, right? So there are different ways to write a linear programming problem. This is just one of the way. And we are before we go to some application, we are going to show that there are different generalized forms to write linear programming problem, and all those forms are equivalent. Okay, so that leads me to the next slide. So exactly as Ari has suggested, you can reformulate the linear programming in this very succinct form. Right? You just concatenate all the constraints into a single matrix. Let's call it A matrix. Then all the constraints can be written as AX greater than or equal to B. Right? Or of course, these 2 are equivalent. Right? AX less than or equal to B is equivalent to AX greater than or equal to B is equivalent to AX less than or equal to B. You just multiply them by -1 on both sides, right? Then you got this generic form. So why this is a case, right? So let's do some very simple manipulation of those constraints. Remember, the first set of the constraint we have in the previous case is AI transpose X greater than BI for all I in M1, right? then for this set of the constraints, there is nothing we have to do, right? They are already in this AX greater than equal to B form. And the second type of constraint, remember the original constraint we have is AI transpose X less than equal to BI for all I equal to, belongs to the set M2. And in order to write it into greater than equal to form, you just multiply -1 on both sides. Then they will be equivalent to the minus of AI transpose X greater than equal to minus BI, right? Okay, so we just want to manipulate the constraint such that it is in this greater than equal to form. And there are some equality constraints as well, right? So we have AI transpose X greater than equal to BI for all I in M3, right? For this equality constraint, you can also convert it to greater than equal to form, right? And equality is just one greater than equal to constraint and a less than equal to constraint, right? So this will be equivalent to having this constraint and also this constraint hold together, right? And then we have some variable bounds. If xi greater than equal to 0 is already in the AX greater than equal to B form. There's nothing to be changed. If it's xi less than equal to 0, we can just write it as minus xi greater than equal to 0. So basically, as you can see, for any types of constraints, we can always manipulate that such that it will be converted to this type of generic matrix form, right? Is it clear for this part? Okay. Yeah. And you might see different forms of linear programming problem. This is one of the form of linear programming problem. So here's just a rewrite of what I just covered. And there are people who would like to write it in a slightly different form. It is called a mixed form of both equality and inequality constraints, where they want to separate the linear equality constraint and the linear inequality constraints, right? So the way to do it is also very simple. Right? You just keep the equalities as one set and the inequality as the other set, and use a different name of the matrix to represent those inequalities. Okay, so one of the forms that needs special attention is called standard form. The reason this form is important is because the algorithm for linear programming is based on the standard form. Okay, so what the standard form says is I only have a bunch of linear equality constraints written in terms of AX equal to B. And I will put all the inequality constraints as X greater than equal to 0. So in other words, there are only non-negative variables in this linear programming problem. There are no negative variables in this problem. Okay, why you can convert in this form, you will see that in a second. Okay, and why this form is useful, you will see that in 2 lectures from now. Okay, but I just first want to convince you that any linear programming problem can be converted into this standard form, where typically, let's say, X is in Rn, A is a matrix such that it has M constraints and N variables. And B is the right-hand side vector of dimension M. Okay, so typically we assume that the rows of A are linearly independent. Why that is a good assumption? Because if you have some linearly dependent constraint, that means one constraint can be written in terms of all the other constraints, right? So that means some of the constraints are redundant, either redundant or there are some conflicts right? If you write one constraint as a linear combination of some other constraints, if the right-hand side are the same, then you have a redundant constraint. You can just remove that. It doesn't affect your problem. On the other hand, if you take some linear combinations of the rows of the A and doing the same linear combination for the right-hand side of B, and then if you got different right-hand side, that means you have a conflict in the system, right? You have an infeasible problem. That's why we usually assume the rows of A are linearly independent. Let's say you have a smart way of removing all the redundant constraints. Okay. And typically, if A is linearly independent, we have M less than equal to N, strictly less than equal to N, right? Why that is the case? Because if you have linearly independent constraint, a row rank and the column rank of the matrix are the same, right? So you can only, if you have only n variables, the rank of A can be at most n, right? So in other words, the rank of A can at most be n, right? So M should be less than or equal to n, okay? Then also I'm arguing that for most of the problem, M is strictly less than n. Why that is the case? Because if you have M equals to n, you are not solving optimization problem. You are just solving linear equations, right? Which is a boring problem. Of course, in this class, we are not talking about solving linear equations. Your linear algebra professor have already taught you how to solve linear equations, right? So if M equals to n, you just have an n by n matrix which is non-singular, right? Then B is just equal to, so if M equals to n, then the only solution to this problem is A inverse times B, right? You have a unique solution, a square system. You don't need to solve an optimization problem, right? There's nothing to optimize. That's why you can safely assume for all the applications we deal with, we have M strictly less than or equal to n, right? Okay. So now the next topic we are going to talk about is how do you really convert a generic linear programming problem into the standard form? So that's how we are going to do that. So first of all, let's think about how far a generic linear programming problem is from the standard form, right? First of all, we need to recognize that in the standard form, you only have non-negative variables, right? But in a generic linear programming problem, you can have some free variables. They are unrestricted in sign, right? For a generic linear programming problem. Then the way you do that is to split this unrestricted variable into two parts. You call it xj plus and xj minus. You can always replace a free variable by xj plus minus xj minus, right? Where xj plus and xj minus are both non-negative, right? So since those two non-negative variables are free, right? Then essentially this part will represent any unrestricted variable if you are free to choose them arbitrarily. Okay, let's spend some time to absorb that. Any questions here? Yes?
Why? I guess what's the motivation behind doing that?
Yeah. So the motivation in doing that is we want to convert it to the standard form. The reason we want to convert the standard form is you will see that in 2 lectures from now. Okay. Yeah. The algorithm for solving linear programming problem is dependent on the standard form. Usually you just assume you have a standard form to start with. Okay. But here I'm just going to talk about in general all the linear programming can be represented in different form. Okay. Yeah. Of course, that's a very trivial conversion, right? You are kind of replacing one variable with 2 variables. What's the benefit of doing that? The reason is that we want to convert to the standard form for the so-called simplex algorithm. Okay. So that part we handle the free variables. And then we also need to eliminate the inequality constraint, right? Because if you check in the standard form, the only inequality constraint we have is this x greater than or equal to 0. All the other constraints are equality constraint, right? So we need to eliminate those inequality constraint. For example, if you have a less than equal to constraint, you can always add a slack variable. That's called the slack variable Si, right? So since this guy is a less than equal to constraint, if you add a non-negative variable to the left-hand side and put a strict inequality here, these two forms are equivalent, right? Yes?
So is xj plus greater than xj minus, or like how are they related?
Oh, so they are kind of unconstrained. The way you argue that is that for any free variable, for example, if you pick a free variable, let's say -5, right? You can always find xj plus xj minus that are equal to. There are multiple. It is not like a one-to-one mapping. The only thing you need to show is that there exists something that will reproduce a real number. Okay, there are multiple ways. Okay, so here with this inequality constraint, you can add a slack variable to the left-hand side to get the inequality, right? And you need the S to be greater than or equal to 0, which hold true, right? This part is in the standard form because you have equality constraint, and all the inequality constraints are a variable greater than or equal to 0, right? And similarly, if you have greater than or equal to constraint, you can minus a slack variable on the left-hand side to convert it to a equality. Okay, this is just a very trivial way to manipulate that into a standard form. Okay, we will have an exercise in homework too. You can take a look. The only step you need to take are those steps A and B. Okay. Any questions here? Okay, so that's all we want to talk about for how to convert linear programming into different forms, right? To summarize, there are, let's say, you will see different forms. Let's say AX less than or equal to B is one of the forms. And then you can also do AX equal to BX greater than 0. That's like the standard form. You can also separate the equality constraint and the inequality constraint and so forth. There are different forms to represent a generic linear programming problem. Okay? Yeah. So the rest of this lecture is only about applications. There is no math in this lecture, so you can sit back and relax. There will be no proofs and so forth. Okay. So let's motivate linear programming problem using some engineering applications. Okay, so here's a very generic problem you will encounter in a lot of disciplines. So it's called a production problem where a firm produces n different goods using m different raw materials. Okay, and then let Bi be the available amount of raw materials, and the J's good, they are like say n goods, and then m raw materials. If you want to produce the J's good, it will require Aij units of the raw material, and results in a revenue of Cj per unit produced, right? And the firm faces a problem of deciding how much each good to produce in order to maximize its total revenue. Okay. So you will see a lot of those planning problems across different industries, right? Typically, each of the company is kind of resource constrained, right? You only have, let's say, the notation here is, so BI, right? So you only have BI resources for different types of resources you get, right? And then if you want to make some products, you need to consume those resources, right? So you have to satisfy those resource constraints while maximizing your total profit. So this can be formulated as a linear programming problem, right? You can just make some variable xj being the amount of the J's good you want to produce. And the problem can be formulated as follows. You are trying to maximize your total revenue, right? So your total revenue would be the revenue from each of the good, and you sum them over. You have n different goods. That's why you sum over Cj xj. And the constraints are the resource constraint, right? You have m different type of resources. You have to make sure the resource you consume for each type of the resource has to be less than or equal to the amount of resource you have, right? Okay. So if you look at this problem, it has a very similar structure to one of the previous application we covered, which is the knapsack problem, right? So this constraint, if you look at it, it's very similar to a knapsack type of constraint. So you can think about the BI being the size of your backpack, right? You can only pack this amount of good into a backpack. And on the other hand, you are trying to maximize the total value of the items you pack into your backpack, right? It is very analogous to a knapsack problem. But here we are talking about the linear programming problems. In the knapsack problem, you are talking about a binary problem, right? Whether you add this atom into this backpack or not. Okay, and you will see a lot of those constraints with similar structure in optimization, right? All those AJ are non-negative numbers, X are positive number, and usually the right-hand side is the resource you have. Okay. Any questions for this formulation here? All right. So let's talk about a very specific example, a farm planning problem. Let's say a farmer has a piece of farmland with L square kilometers. So that the land is one of the limited resources the farmer has, right? And the farmer can plant either wheat or barley or some combinations of two. And it also has a limited amount of fertilizer, F kilograms, and pesticide, P kilograms, right? So in this problem, there are three different types of resources: the land, the pesticide, and also the fertilizer, right? And if you are there are two types of goods the farmer can produce, which would be the wheat and the barley. Okay, that's just an instantiation of the problem. And then you can define those variables here, their selling price for those products, and then the requirements. The variables we can have would be the area of land planted with wheat and barley. You can denote them by x1 and x2. The objective is to maximize the total profit from those two different products. And you have three types of constraint because you have three resources that are constraining the farmer: the total area, the fertilizer, and the pesticide, right? That's just a toy problem of the production planning problem, okay? Yeah. So since it's a two-variable problem, we can give you some geometric intuition on how this problem works, right? So remember that we only have x1 and x2, two variable, right? The area you are going to grow wheat, and the area the farmer is going to grow barley. Then we can plot the feasible region on a 2D plane, okay? So let's try to think about all the constraints, right? So the first constraint was written in red. And if we're going to plot it, it will be this red line here, okay? And then this constraint will denote the feasible region below this line, right? Because it's a resource constraint, the land you have has to be less than or equal to this. And the second constraint, I think it's a constraint on the pesticide. It is denoted in blue. That will be this particular line here, right? The feasible region will be, below this line here. And the third constraint is denoted in green. That will be this line here. Okay? So with those three constraints, and also, of course, X has to be non-negative, right? You cannot plant a negative acres of wheat and so forth. So with these three constraints, we can draw the feasible region. It will be let's see. Okay, so it will be, okay, this, hopefully it is clear on the board. It will be this region with the, right? It has, let's see how many, 5 edges, right? Okay. And now you can solve this problem geometrically, right? So here in this problem, they have plotted this contour plot. As you can see, those dashed lines are the contour plots of this problem, right? And one of the important observations we can get is the optimal solution of this problem is at one of the vertex of this polyhedral, right? Okay, so if you plot the contour plot, it's like you are, let's say, you are gradually moving this contour plot up, right, to see where you hit the boundary. Then if you move this way, you are increasing the total problem, right? And you want to move this boundary as much as possible, right? And then you can only move the boundary until the point here, right? There is only one feasible point. If you continue to move up, there will be no feasible point. Okay. So one of the things you can observe in this problem is that the optimal solution is obtained at a vertex, right? It is at this this black dot here, okay? So is this a coincidence? Are all the optimal solutions of a linear program lie at a vertex, right? Is that the case? We can think a little bit about that. Actually, we will cover this in the next lecture. We will show that for all the linear programming problem, as long as it has a solution, the optimal solution will be at a vertex. Okay, that's a geometric way of interpreting the optimal solution of a linear program. Okay, we will show that in a very mathematical, rigorous way, but you can get some intuition from this problem just by moving the hyperplane of the contour until there is no feasible points. You cannot move up. Okay. Yes.
What would be in this case the geometric interpretation of the slack variables?
The slack variables. Oh yeah, so we do not have the slack variables in this case, because we are just plotting the x1 and x2. If you add the slack variable, it will be in a very high dimension. We don't know how to view.
Yeah,
right?
That's my question.
Uh-huh.
Do the slack variables increase the dimension of the problem?
Yeah,
Or
it
is more
does.
like how we move in the geometry, in the space of the problem.
Uh-huh. Yeah, so the slack variable does increase the dimension of the problem. But here in 2D, you can define a vertex. Yeah, everyone knows intuitively what a vertex is, right? But how do you define a vertex in high dimension? So in the next lecture, we will show that even if you add the slack variable, you can define vertex in an algebraic way such that you will also hit a vertex in high dimension. Okay. Any other questions here? All right. So let's talk about a different problem. Do not look at the text here. It's too congested. So it's called multi-period planning of electric power capacity. So this is something I have worked on personally during my PhD research. So if you think about the power system here in the US, they get blackouts from time to time, right? If you read the news in Texas, they get blackouts with extreme weather. The reason is that sometimes we do not have enough capacity to satisfy the demand. So the problem that those central coordinator, for example, if you, let's say for the sake of the argument, if you live in Texas, then they are solving a planning problem to expand the power generation capacity such that when the population grows and the demand for power grows, you still have enough generating capacity to satisfy all the load such that you don't get a blackout, right? So this is a similar problem to what those people are solving, okay? So if you read the problem here is, let's say if a state has a forecast of DT megawatts. For example, the demand will keep growing. You can think about the time T as a year, for example, right? From here, from now to 2050, we need to have a plan to expand the generating capacity of the electric power system, right? So, of course, this problem is a simplification. It just assumes the existing capacity are all oil-fired plant that will not be retired. So the oil plant will still be operating. There are two alternatives for expanding electric capacity with coal-fired or nuclear power plant. Okay, so as you can see, this problem, it must be really old. No one is talking about coal-fired power plant nowadays, but let's assume that this is the case. And there will be a capital cost CT per megawatt of coal-fired capacity to be operational at the beginning. Of course, if you are going to build new coal-fired power plant, you need to put the money in building that, right? And similarly, if you have nuclear power plant, the capital cost is NT, right? And for the sake of the argument, for some political and safety reasons, it has been decided that no more than 20% of the total capacity should be nuclear, right? And nowadays we have similar constraint. We want to get, net zero carbon emission by 2040 or something like that. Right? And coal plant lasts for 20 years, and nuclear plant lasts for 15 years. And we want to get a least cost of capacity expansion plan to satisfy the demand, right? A lot of industry have to solve the similar type of problem as long as their business is growing, right? If you are talking about a chemical plant, you want to expand the capacity of your chemical plant or your warehouses for companies like Amazon or those delivery companies, okay? So how do we formulate this problem? I have outlined those parameters and variables in tables. So T is the number of years we are considering. The DT is a forecasted demand in year T. ET is the existing capacity. CT and NT are the capital costs for the coal-fired power plants and the nuclear power plant. The variables include the coal capacity brought online in year T, the nuclear capacity brought online in year T, and then the total coal capacity, because the coal and the nuclear capacity can retire, right? It only has, if you look at the problem, the nuclear plant lasts for 15 years, and the coal plant lasts for 20 years, right? So you need to consider they may retire when the number of years is too long. Okay. So with those definitions, if you forget those definitions, that's fine. Once you read the constraints, it's quite intuitive. First of all, the objective would be minimizing the total cost, right? There are only two types of capital cost. We are investing in both coal and nuclear. So we are minimizing the total cost here. And then we need to calculate the available coal and nuclear power plant at a given year T because they can retire, right? So in order to do that, it will be a summation over all the coal power plant you built in the previous years if the number of years is less than 20, right? So if the number of years is less than 20, no coal-fired power plant will retire. So you just sum all the coal-fired power plant you built in previous years. And on the other hand, if the number of years is greater than 20, then we will only sum up the plant that have not retired. Okay, that's what this max 1 and T minus 19 means. Okay. And similarly, we can do it for the nuclear power plant. And after that, we need to satisfy the demand constraint. The W, Z, and ET are all the power plants that are still operating at a given year. They have to be greater than the demand, okay? And the last thing we need to satisfy is the nuclear capacity. we said the percentage of the nuclear capacity has to be less than 20%, right? So if you take the percentage, which can be calculated this way, it is less than 20%, but this is not a linear program, right? You have like a fractional term. It is very undesirable, but if you multiply this to the right-hand side of the equation, you will find that you get a linear constraint, right? Any questions for this problem? Yes?
Can you explain the t minus 19 and the t minus 14? Like
Yeah.
Mathematically?
Yeah, sure. So let's say when t is let's say less than equal to 19, right? When you have a t less than equal to 19, then no coal-fired power plant have retired yet, right? So you just sum over all the previous new coal-fired power plant you built, right? So here, when you take the max over 1 and t minus 19, then the max is always 1, right? So you just sum from 1, okay? But let's say if you have, so for the 20, the max 1 and t minus 19 will be equal, it doesn't matter. But let's say if you have t equals to 21. So in that case, you don't want to account for the coal-fired power plant you built in the first year, right? Because they have already retired, right? Then you take the max of 1 and t minus 19, it will be 2, right? So you just sum the coal-fired power plant you built from the second year to the 21st year. Yeah.
So would each like t be its own separate constraint?
Yeah, exactly. Yeah, so that's why we say it's for all t from 1 to capital T. You all have this constraint. Other questions? Okay, so let's continue then. Yeah, so this is a problem probably only chemical engineers know what I'm talking about. How many non-chemical engineers are in the audience today? Okay, yeah, so let me explain what this is. It's very, very simple. So this when you talk about the CSTR, all the chemistry students know what that is. So a CSTR is it's like a chemical reactor. Okay, so let's say in a chemical reactor, in a very simple case, you are trying to produce chemical C from chemical A and B, right? And then you can feed those chemicals into those reactors continuously. Suppose there is there are some flow rate. You are kind of pumping some flows of chemicals into the reactor. And the continuous stirred tank reactor means this reactor are fully stirred, meaning that the concentration at this reactor are uniform. Right. For example, the concentration here on the surface are the same as concentration here. It's a very extreme simplification of a reactor. Of course, if you do not stir it very well, the concentration at different locations of the reactor would be different. Okay, yeah. And some of the chemical reaction, it can be exothermic. Right. You need to remove the heat from the reactor, otherwise the reactor will explode. Then that's why here this TC thing is like the cooling water you want to inject to this reactor just to keep the temperature constant, because some of the reactions are exothermic, right? You do need to take the heat away using cooling water. And then the problem we want to solve is we want to keep this reactor to run at a steady state. You don't want the concentration of the reactor or the temperature and the height of this reactor to change, right? So this is a so-called control problem, right? You want to have some sensors to measure the temperature, the height of the fluid in the reactor such that they are at steady state, okay? So although this is a chemical engineering problem, the methods I talk about will be valid for all the control problems. Maybe in aero you will have problem like you want to control a rocket to land at a given location, right? Or maybe you want to control a robot to do certain things, right? So those are all control problems. Okay. So in order to model those chemical reactors, typically people use some ordinary differential equations. Right? If you think about, let's say in aerospace, you also model system using ODEs, right? Like if you want to model the dynamics of a rocket, you have a bunch of ODEs to model that, right? So here, those ODEs describes how the concentration, the temperature, and the height of the reactor change with respect to time. You don't really need to worry about the left-hand side, right? I'm not so good at physics. Let's just talk about the math here, right? So there are some things govern the kinetics and the thermodynamics of those reactors, right? So you can say, if you change the cooling water, those ODEs will reflect how the temperature of the reactor will change, and so forth. Okay. So any questions related to the, the setting of the problem itself? Is it clear that the idea is like you have, yes, go ahead.
I was going to say, could we add another variable in if this was going to be used for biological growth?
Yeah, sure. You can also model things like biological growth in this type of form, right? As long as you know the physics of the system, you can model them using ODEs. Okay. So the idea is that you have some equations to describe the dynamic of the reactor, and then maybe there are some fluctuations in the reactor. You want to control them at a given steady state. You don't want the concentration of the reactor to deviate a lot from a given set point. Okay. So the way to do it, there are different ways to do it. We are going to talk about the linear programming way of solving this problem. Of course, you can directly try to optimize the ODE, right? So there is a branch of optimization that talks about, how do I solve optimization problem with differential equation constraints? Those are very hard optimization problem to solve. So in this class, we are not going to talk about that, right? We will only solve optimization problem with algebraic equation constraints. Okay, yeah. So how do we simplify this problem a little bit, right? So again, the motivation is that the ODEs are difficult to optimize directly, right? Then the solution people usually come up with is to use a linear model to approximate the ODE, right? So that is an area called model predicted control in control theory. We are not going to go to the details of model predicted control because this is not a control class. If you are into the details of control, there will be some whole semester long class just talk about model predicted control. This is just to give you some flavor how control works. Okay. So here's how it works. You can write this problem in this very generic linear programming problem. Okay. Instead of the ODE, you can write this linear equation constraint. Right? So the xt variable are the states of the system at time t. Okay. What are the states of the system in this case? That would be the measurement you can get from the reactor, like the temperature. For example, in this case, you can think about the states are the concentration, the temperature, and the height of the fluid in the reactor. Those are the variables you can directly measure from the reactor, right? If you go to those reactors, maybe you have some ways of measuring the concentration, the height of the reactor, or you have a thermometer to measure the temperature. That will be the state of this system. Okay, so besides the states of the variable, there is something called systems output. Those are the variables that can be measured. Okay, I take that back. So the x are the variable to describe the state of the system, but maybe not all the states can be measured. For example, you can only measure the temperature and the height for some reason. You cannot directly measure the concentration. Then among all the three variables, you can only measure two of them, right? But if you can measure all the states in this system, then this C matrix would be an identity matrix. In other words, all the variables can be measured. That's what this constraint does. Okay, so the yt equals to c times xt would be describing what are the variables that can be directly measured. Okay, and the ut are the input variables to be manipulated and determine the future state. those are the variables that you can manipulate, like the cooling water rate. You can really control how much cooling water you are going to flow into the reactor, right? That's something you can manipulate through some type of controller, right? Yes.
So is C only containing like ones and zeros within it?
Usually it does, right?
Okay.
Maybe in some other more complicated, yeah. Maybe we have some control experts in the audience. Any, you want to talk about it? The
So
C is-
generally, so at least for the CSTR system, the outputs are the states that we are interested in. So
Okay.
in this case, the C is like the identity matrix where it only has the 0 and 1 value. But for some other systems, like more complex systems, the output could be different from the states. So that will be determined by the C matrix.
Okay, yeah. Right. Then you can think about the dynamics will involve as some algebraic equation instead of differential equation, right? So in other words, in some cases you can discretize a differential equation, right? That's one way to think about that. In other cases, maybe this is just a simplification of what happens, right? So then this equation describes how the system will evolve, right? So the future state at t plus 1 will be a function of the state at t times the A matrix. You can think about A as sort of like a transition matrix from the previous state. Yes?
So when we're linearizing the constraints,
Yeah.
would one case be, so you said one case is to just discretize
The- Yeah.
derivatives, or
Yeah.
would you also be able to do like a first order approximation and use that since it doesn't have any higher order terms?
Uh-huh. Yeah, you can do it both ways. There are maybe more, yeah, there are more sophisticated ways in control to generate those reduced order models. Some of those are even data driven. You can derive those in matrix, but some of those are first principle, like you said. You just derive that from the differential equation. Okay, yeah. And then the next state will be a function of the state at time t plus B matrix times the manipulated variable, right? Because the way you are going to inject cooling water into the system will affect, of course, it will affect the temperature and concentration. That's what this B matrix does. So there are a rich literature discussing about how do you get the A and B matrix. In this case, we just assume we do know a very simple linear model to approximate the ODE that is given to you, right? Where this class is not about getting those A and B matrices, okay? And if you think about other applications, it's not just about controlling a CSTR, it can be control anything. Like, for example, if you want to control rockets, right? The state of the rockets could be the location and the angle of a rocket. Then the manipulated variable could be how much fuel or acceleration speed you want to give to the rocket, right? Such that you can land at a given location. You can always use those type of model predictive control models. Okay, so one of the things in control people like to assume is that at steady state we just assume all those variables equal to 0. Why that is a good assumption, because in chemical engineering, most of the chemical plant operate at steady state, right? Of course, those variables, those temperatures are not 0 at steady state, but you can always, take the temperature minus the steady state to normalize that to be 0, right? That's why it's just for notation simplicity, we just assume at a given steady state, you assume all those variables are 0. And the objective usually try to penalize the deviation from the steady state and the change in the control action. Okay. Besides those transition constraints, usually we have some constraint on the control, on the manipulated variable and on the state variable as well, right? For example, you can have some boundaries on the maximum cooling water you can inject into this reactor, right? You cannot inject infinity amount of cooling water into the reactor. That will be a constraint on the manipulated variable. And sometimes you can have some constraint on the state as well, right? For example, if you are controlling a robot, you don't want the robot to hit a wall, right? That will be a constraint on the state. Okay, and for a chemical reactor, for example, you don't want the temperature to go above a certain threshold, otherwise the reactor may explode. That will be the constraint on the state. Okay. Any questions here? Okay. Yeah.
You might cover this later, but how is that like a linear objective?
Oh yeah. So here, the way we write it as linear objective, I will cover this, how you can formulate this. Usually, you would like to penalize those output variable and the manipulated variable using any certain norm. Typically, people usually use a 2 norm actually, but using a 2 norm would not be a linear programming class, right? So that's why we keep it linear. I will show you how to keep this penalty to be linear later on. Okay, yeah, right. Yeah, so at the end of this class, we will show how to make this objective linear. So here's another very well-known linear programming problem called multi-commodity flow problem. Okay, so assume you have a graph. By the way, in the homework, you are going to see some graph theory type of problem, like you have some nodes you want to cover those edges and so forth, right? Usually, when you represent a graph has 2 types of elements, the nodes and the edges, right? So usually you use the set V to denote the nodes, the set E to denote the set of edges, right? And assume you have some commodities you want to transport across the network. And let's say on the left-hand side, you have a bunch of nodes S1, S2, and S3. So those are usually called the source node. So you can think about they are called the source nodes. And on the right-hand side, those nodes are called the sink nodes. So let's say at each of those source nodes, you have some commodities you want to ship to the sink nodes, right? That's what happens with all those companies like FedEx, right? They have a bunch of commodities at some given location. They want to ship it to some other location, right? And each of the edge has a capacity. For example, if you are going to ship by railroads, right? Of course, the railroads have some capacity. You cannot exceed those capacity. That represent the capacity of those edges. And each of the, if you are using some of the edge, you are going to incur a cost denoted by C sub E. And the commodity has a demand of dk at those sink nodes, right? You're just trying to ship those commodities from those source nodes to the sink nodes such that you minimize the cost. Okay. Yeah, and there might be some intermediate nodes, right? In the middle. For example, if I'm talking about companies like FedEx, maybe they have some warehouses or facilities in between 2 cities, right? You first deliver to an intermediate city, and then you ship it to your destination. Okay, and there are different types of commodities you want to ship from the source nodes to the sink nodes. So how do we formulate this problem, right? So we can use a variable xek to represent the flow of commodity k through edge E, right? And of course, if you are talking about the capacity constraints, if you add up all the commodities at a given edge, it shouldn't exceed the capacity of a particular node, right? Just sum over all the k of xk, they have to be less than or equal to the capacity. The next constraint is a little bit more sophisticated. If you are, if you are a chemical engineer, you can think about this as a mass or energy balance type of constraint, right? For each of the node in this graph, any inflows to this node has to be equal to the outflows to the node, right? Especially, let's say, if a node, if a node is an intermediate node, right? There is no demand associated with this node. Then all the all the inflow to this node has to be equal to the outflow to this node, because this node has no demand. It cannot accumulate any commodity. And on the other hand, if you have some source nodes, then all the edges that going out of this particular node has to be equal to the total amount of commodity it tries to ship out of the node, right? And on the other hand, if you are at a sink node, all those commodity going into this node should be equal to the demand at the sink node, right? So this constraint would be a mass balance type of constraint. If a node is a source node, then what's going, so this SK should be, so what's going in minus what's going out should be equal to the demand of the particular node, okay? And the objective is to minimize the cost of using different edges. Okay. Questions here? And so the other thing I forgot to mention is that each of those edges would be directed, right? There is a particular direction you want to ship those commodity. In some problem, like in this covering problem, the edge could be undirected. You don't need to specify the direction of the edge. In this graph, the direction of the flow has been specified by the problem. Okay. Yeah. So now it comes to the final part of this lecture. We are going to talk about how to formulate a problem with norms into linear programming problem, exactly what you were already asked, right? So recall what we have talked about in lecture 2. Any norm is a convex function for any norms, right? But among all those norms, there are two types of norms that can be formulated as a linear program. And they are the infinity norm and the one norm. Okay, so remember the infinity norm is, let's say x is n dimension. You just pick the maximum value among all the absolute value of each entry of x, right? That's the infinity norm. See, some of you look confused. So let's say we have a vector which is 1, minus 2, and let's say minus 4. What is the infinity norm of this vector? It's 4, right? You just take the absolute value of each entry is 1, 2, and 4. The maximum value is 4, right? And the one norm is the following. You take the absolute value of each of the entry and sum them up, right? That's a one norm. What's the one norm of this vector?
7.
Yeah, that's 7, right? You just sum them up here. Okay, so now I'm going to show some of those linear programming problems that involve infinity and one norm can be formulated as a linear program. Okay, so the first type of problem that can be formulated as linear program is this one. If your objective is a one norm and the constraint is linear, this is a linear programming problem. That's a CSTR problem, right? If you are penalizing the manipulated variable and the state variables by the one norm, then essentially this is a linear programming problem, right? So how do we do that? Okay, so the way we do that is to introduce an additional variable. We call it zi. So recall that, the one norm is nothing but the sum of the absolute value of xi, I from 1 to n, right? So we are going to introduce a zi variable. So we are going to introduce a zi variable to represent the absolute value of xi. We are, since you are minimizing, if you can have zi greater than equal to the absolute value of xi, right? And then you are minimizing, right? Then the I will always be equal to the absolute value of xi in this problem, right? Okay. So the way to do that is the following, right? how do we model that zi has to be greater than equal to the absolute value of xi? So xi can be either a positive or a negative number or 0, right? So the way to do that would be very simple. You only need two constraints. If you let zi greater than equal to xi and zi greater than equal to minus xi, then I can argue that zi is always greater than the absolute value of xi, right? So if xi is a positive number, you have this constraint saying that zi has to be greater than equal to xi. If xi, let's say, is a positive number. If xi is a negative number, then the absolute value of xi is minus xi, right? And then you have this constraint to enforce zi to be greater than equal to the absolute value. That's just a very simple way to say that. And you need to do that for all the I, since it's a one norm. Xi is the summation of absolute value. Okay. Yeah. Is this part clear? Yes.
Why do you need to create the new variable? Because if like the one norm is just a summation itself,
Yeah.
then isn't that like inherently linear, I guess?
Yeah, but then for linear programming, you can only write the constraint like A transpose X greater than or equal to B, right? The absolute value is not in this form, right?
Okay.
Because the absolute value, you need to flip the sign of a negative number to a positive number. There is like some sort of conditional thing there,
Okay.
right? Yeah.
Why don't you just like set zi equal to like
Mm-hmm.
the absolute value? Or
Yeah, so you have to convert the absolute value into some linear constraint, right? The absolute value itself is not a linear constraint, right? It's a function per se, right? The function of x which is not linear, right? If you write out the function of the absolute value of x, you can see if this is 0, this is x, then the absolute value function is something looks like this, right? This is not a linear function. You have to convert this into a linear constraint representable form per se. Okay. Any other questions here? Yeah, so maybe now I can ask you guys a question. If I change this problem to a maximization problem, is this a linear programming representable problem? Right, let's say if this problem is max over the one norm of x subject to ax less than or equal to b. Is this can this be represented as a linear program? Yes.
You can just minimize the negative of the one norm, or you can set change what your b is to
mhm.
negatives. That way everything stays at the same
Uh-huh.
size.
Yeah. Yeah, you can try that and see what happens. Yeah, any other thoughts about this? So recall that what we have done here is that the zi is not exactly equal to the absolute value with our modeling here, right? We can only argue that zi is greater than or equal to the absolute value. Since we are minimizing this, is fine, right? So if we are minimizing, then the zi will always be equal to the absolute value, right? But if you are maximizing, zi will be unbounded here, right? It will not be equal to the absolute value of x. Yes.
why can't you just like flip the sign of that inequality?
Flip the sign of the
Like zi is less than or equal to.
the I less than. Okay, yeah. Let's do a very, very simple problem, then you will see. So let's say I have a very naive problem, right? Let's first do the minimization. Let's say x is only one dimension, okay? X is just we are minimizing at the absolute value of x. Then let's say x is from -1 to 1, right? Okay. Then it's very clear that the optimal value of this problem is 0, right? So let's say if we formulate it as linear program, it works, right? We are just minimizing z such that z is greater than equal to x, and d is greater than equal to minus x. X is from 0 to 1, okay? Yeah, and these two formulations are equivalent when you are minimizing, right? Because you can take x to be 0, and then the minimum is 0, right? Okay, so let's say if we are maximizing the absolute value of x is 1 to 0. It's very clear that the maximum value here is 1, right? Okay. So now let me follow what you guys was telling me to write this. Try to write this as a linear program. Yeah, I would just listen. What do you also want to do? Maybe maximize. Maybe Zach, do you want to write it down here? or you can just read. Just tell me what I should write. The objective would be what?
I'm sorry, I don't understand what you're asking.
Oh, okay. Yeah, so it's just like I'm changing this problem into a maximization of an absolute value problem, trying to argue whether you can formulate as a linear programming problem or not. Okay.
Yeah, well, I was saying before was because linear programming requires that you write it as a minimization.
Mm-hmm.
And so just that the negative of a minimization is...
Yeah, so I want to get a coefficient of maximization problem with the positive sign. Or maybe I'm talking about this problem here. Or this problem, these two problems, whether they are linear programming representable or not. Okay. So you'll find out quickly that this problem is not linear programming representable. Okay, because because it is a maximization over absolute value. Let's say we haven't changed the constraint. We only changed the objective, right? Let's say we do the same trick if we are maximizing z, and z greater than or equal to x, z is greater than or equal to minus x, and minus 1. Okay, so what's the optimal value to this problem? It will be infinity, right? Because you are maximizing, and then kind of z is unconstrained. So the optimal value of this problem would be infinity. Okay. And there is another way you can see it doesn't work, is because if you take a look at the function of one norm, right? This one norm is a convex function, right? So when you minimize a convex function, it is a convex problem, right? But if you are maximizing a convex function, it is no longer a convex optimization problem, right? So since linear programming problem is convex optimization problem, right? So there is no way you can represent a non-convex optimization problem using linear program. That's another way to view this. Okay. Yes.
So I see that it's unbounded, but is it possible to use like a trick, like n minus the norm?
Yeah, you can try the trick after class, then you will quickly find out that there is no trick you can formulate as a linear program. Yeah. So there are some fundamental limitations where you can not just write it. Okay. So similarly for infinity norm, if you are minimizing an infinity norm, then you can represent as a linear program, right? Linear program, infinity norm is also a convex function. When you are minimizing infinity norm, it is convex. Okay, so the way to do it is that we introduce a new variable t such that since you are taking the maximization over all the absolute value, right? You just write t greater than or equal to the absolute value of xi for all I, right? And you can do the similar trick to write those constraints here to represent the infinity norm. Okay, so I want to go to this is the last slide. So there are other, if some of the absolute value is in the constraint, you may also represent it as linear program. Let's say if you have a less than equal to constraints, where all the AIs are greater than equal to 0, and this is linear programming representable. Okay, and you can have a similar trick to introduce a variable zi for each of the xi's and make them greater than equal to xi and greater than equal to minus xi, and they sum up with the zi. They have to be less than equal to b. Okay, so note that in order to be linear programming representable, the key here are two conditions. One is all the AI are greater than equal to 0. The other thing is this is a less than equal to constraint, right? If you do not satisfy any of those conditions, it is not linear programming representable. Okay, why that is the case, you can also think about in terms of convexity, right? So each of those absolute value functions, okay, sorry, I'm going a little bit over time, but I want to finish this. So the argument is that the following from convexity, right? So each of these functions, let's say xi, the absolute value of xi is a convex function, right? It's very easy to see that. You can very easily prove that. It's like a one norm of a single variable, right? So xi is, the absolute of xy is convex, and for all I from 1 to, right? And then if you are taking the weighted sum of some convex functions, right? If you are taking some non-negative weighted sum of convex function that preserves convexity, that is one of the homework problems, right? You will find out this, there is a property here. So let's say if you have some functions f1 all the way to fn being convex, and if you take the weighted sum of those functions ai, fi, I from 1 to n, this function is also convex if all the AIs are greater than 0. This is a homework question you guys are going to prove, right? So here, as you can see, we have some weighted sum of those absolute value functions. They are all convex. That's why this whole function on the left-hand side is a convex function, right? And if you put that into a less than equal to constraint, that gives you a convex constraint. If you change that to greater than equal to, that will be a non-convex constraint. Okay, that's why you can kind of intuitively see why this can be formulated as a linear programming problem. If you change the condition of a little bit, it will no longer be able to be formulated as a linear programming problem. Okay, and then for more details, you can check this linear programming textbook. Right? Any final questions? Yes.
So if you have something that's convex but non-linear, can we use like something basic like Euler's method to make it linear and just have it be like an approximation of the optimal solution?
I see. You are saying like if you have a nonlinear problem, how do you use your linear programming techniques to solve that? Yeah, so that is some techniques we will cover towards the end of this semester called outer approximation methods. Yeah, exactly what you said.